Hello everyone! Recently in the Port programming language, the stack-based programming language that I'm developing, we implemented a new way of manipulating the stack. So historically, we sort of inherited the stack manipulation paradigm from Forth, and in Forth you basically have several words that manipulate the stack. So let's take a look at how we usually do that. So let me open some sort of example. Let's create a file. Main port, I'm going to include the standard library, right, and I'm going to provide the entry point, and there we go. So I don't really remember how many stack manipulation words we have in port, but I can always look it up in the source code. So all of them are intrinsics, right? All of them are intrinsics, and I think this is where they start. Print, it's kind of a stack manipulation word because it's like printing whatever you have on the stack, but let's not include that. I think we have like around like 5 stack manipulation words. Forth has more of them, but I've been using only those, and those are dupe, swap, drop, over, and rotate. So essentially how they work, dupe essentially duplicates whatever you have on the stack. If you have some sort of element A on the stack, it pushes the copy of that element on top of the stack. Swap, it operates on 2 elements on the stack, so if you have A, B, it swaps them, making them BA. Right, drop drops the element on the stack, so if you have something like A, it will not exist on the stack anymore. Over is like dupe, but it copies the element over the top of the stack, right? So if you have AB, you're going to have ABA. So as you can see, it reached the element over the top and put a copy of it on the like on top of here. And rotate basically rotates 3 elements on the stack, right? So if you have something like ABC, it brings this element to the top, making it BCA. So this is the words that we're usually using, and the entire compiler actually implemented using these 5 words. Forth obviously has more words. I never looked into them. Maybe some of them make some things convenient, but in any case, I find this paradigm of stack manipulation is quite frustrating, right? Because what you end up with is like, even for a simplest task, you end up solving a puzzle, right? So you just want to do some simple things, and you have to keep track of the state of the stack in your head and just like look at these pieces and just think like, how do these pieces fit together? Maybe you can get used to that, and over time you can just do that. But for how long I've been actually developing this thing, I don't remember. So let's actually take a look at the log. And I've been developing that from since the September 8th, right? And I implemented the whole compiler using that style essentially, right? And the whole compiler is like 5,000 lines of code, so I can program in that style, right? I can accommodate for that style. But even after all of that, after all of the month of development and like this code base, I still find it frustrating. Like, I don't like solving puzzles while trying to solve an actual problem, right? It just like adds a new, like whole new layer on top of the problem that I'm currently solving. So for example, if I have 3 elements on the stack, right, 10, 20, 30, right, and I want to print them, if I do something like print, it will print them in a reversed order, because on the top of the stack we have 30, then 20, then 10. So let's actually see how it works. All right, so as you can see, it prints 30, 20, and 10. If I want to print them in a reversed order, it kind of becomes difficult, because how do I reach this element, right? So I don't have over that copies the element over, so I have to use rotate, right? So, and that will make the stack look like 20, 30, and 10. You see, I'm already have to keep track of the state of the stack. Like, why do I have to do that? I don't understand. But anyway, then I have to do print, and that basically removes this entire thing. And then I have to print this one. So in that case, I have to use a different word, which is swap. That will swap it around and then print it, and then I can print it again. So there we go. go. So that way I can print them in a reversed order. So as you can see, such a simple task as just printing them in a different order already requires me to keep track of the stack in a comment here. Well, maybe it is fine for some people. Maybe some people can do that. And I'm not saying that you shouldn't do that if you enjoy this way of programming. What I'm saying is that I personally don't find this way of programming enjoyable, even after doing it for several months and implementing like 5,000 lines of code, actually more because there's more code outside of the port compiler. I still don't enjoy this style of programming because quite often, like I know where the element is located on the stack. Right, so the element that I want to work with, I know where it is located on the stack. I just want to reach that element directly and do something with it directly. And that's exactly what I implemented, right? I implemented a feature that allows me to do exactly that. And I present to you let bindings, right? So you start with the keyword let, and you provide the names of the variables. In that case, we're going to say A, B, C, right? And then you say in, indicated that you're done listing elements, and then you start the block and you end the block in here. What this thing does, right? As you can see, we have three names in here. Let operation sort of like takes three elements on top of the stack, removes those elements from the stack, they're not on the stack anymore, and it binds them to these names. And the next time within that block you use that name, you're pushing that element back onto the stack. So if you want to print them in whatever, like in the order that they were pushed, you would just do A, print, B, print, C, print, and that is it. You don't have to think about rotation, swapping, or anything like that. You just say, okay, I have three elements, bind these three elements to these names, and let's just work with these names. That's it. As simple as that. And what's interesting is that with these let bindings, you can kind of roughly implement all of these operations and even more, right? If you want to duplicate something, you would say let A in, and just like that. And it looks exactly like the classical fourth signatures, right? So you have that. If you want to swap the elements, you will do something like this. Here is your swap. If you want to drop the element, you will just do something like that, because that will basically bind this element into a name, and then at the end that name is going to be dropped. If you want to reach the element over over the top, you would do it like this. And if you want to rotate something, you would do it like this, B, C, A. And what's cool is that you don't really have a limit, theoretically. Theoretically, you don't have a limit on how many elements you can access in here. So if you want to just reach the element in here, the sixth element, you can simply do that if you want to, right? So you're not limited with these specific hard-coded words. You can basically decide however you want to manipulate the stack. So that's basically the let bindings. Of course, all of these words still work in a code base, and because in some situations they're very useful because they're short. So essentially, like, let bindings are kind of like syntactically noisy, right? So you have to decide whether you want to pay for the convenience with a little bit more syntactic noise, or maybe not. So I'm not going to remove these words from the language yet. But we'll see how it goes. And maybe in the future, all of these words can be implemented using let bindings, but we still lack a couple of like type system features to make it possible. So for now, they're hard-coded in the program, in the compiler. So yeah, that's basically let bindings. So let's actually take a look at more, concrete examples of how you can use let bindings. Maybe some simple algorithms. So I think the first thing I want to implement Fibonacci number generator, right? So the classical algorithm, and use specifically let bindings for that. So we usually start with pushing first two numbers of Fibonacci sequence. It's a 0 and 1, right? And while this element is less than some n, we're going to keep looping and generating more and more Fibonacci numbers. So for example, in this specific case, it is easier to use over just to check that this element in here is less than, let's say, 100, right? So in this specific case, like, using let bindings is kind of meh, right? Because in that case, look how it's going to look like. So we'll have to do something like let, AB, then I will have to do A 100 less. And since A and B are removed from the stack, but I still want to keep them on the stack, I'll have to kind of like push them back, but then it will obscure the Boolean in here, so I'll have to put it somewhere in here. So it's going to be A and B, and there we go. So as you can see, sometimes it is not convenient, and that's why I'm not removing these words, these fourth words yet, right? So I think there is a place for let bindings and the fourth style of development, right? For quick things like that, for small quick things like that, I think fourth is okay. But within the while loop, I think we're gonna use the let bindings, so we can have A and B. And the first thing I want to print this element in here. So I'm gonna do A, print, and there you go. And then I want to generate the next pair of Fibonacci numbers. So the next pair is gonna be B, and then A plus B, and that's it. I didn't have to think about the stack too much, right? So I just grabbed two elements on the stack and I directly manipulated them and I pushed them back. And the cool thing about let bindings is that they don't break existing language. Everything that worked in Port before still works with them. It's just like a new feature on top of it, even though it kind of makes the language feel slightly different, like it feels like a completely new language, but it's still concatenative, it's still stack-based, it just like lets you more directly manipulate the stack and also assign names to the elements. And after that, you want to drop the elements in here. So there we go, we generated Fibonacci numbers. We can now try to run this entire thing, and here they are. Here are the Fibonacci numbers. So pretty cool, huh? So let's actually move this entire thing into separate procedure. Right. And let's think about other examples. I think the next example that I usually struggled with, I remember when I only started to implement Porth, I really struggled with implementing str equal, right? Str equal essentially takes two strings and answers whether they are equal or not, right? So you would use it like this, hello world, strq, and then if they're equal, you would do something, right? The strings in Porth, they actually push two values on the stack. They first push the size of the string and then the pointer that points to the beginning of the data of the string. So they're size strings. So because of that, this entire thing is going to accept two values, integer and pointer. So this is the first string, S1, and this is the second string. And then this entire procedure is going to return Boolean, indicating that the strings are equal or not, right? And I couldn't implement this procedure without having some sort of like an intermediate memory, right? So, and the question is, could it be implemented using let bindings without any intermediate memory, like, you know, local memory blocks and stuff like that? So, and the answer is yes. The answer is actually yes. So let's go ahead and implement that. So let's organize the while loop. And in the while loop, we're going to keep iterating while the characters are equal to each other. So essentially, we're going to be looking at the first characters of the strings. And if they're equal, we sort of chop both of the strings by one. And then on the next iteration, look at the first characters again and again until one of the strings becomes empty, right? And then after the loop, we look, are they both empty? If they're both empty after this truncation, that means they're equal. If they're not empty, that means they're not equal. So that's basically the entire algorithm. All right, so let's go ahead and bind their values to some names, right? So we're going to say this is the size of the first string, and this is the pointer of the first string. This is the size of the second string, and this is the pointer of the second string. Right, and in here, what we want to do, we want to check if they're both not empty. So n1 has to be greater than 0, and n2 has to be greater than 0, and both of them has to be greater than 0. And if this is true, we're going to continue doing some other things, and if this is false, we're going to return false. Right, and in here we want to take a look at the first characters of both of the strings. So we're going to take first pointer and read the character out of it, the second pointer, read the character out of it, and compare them. If they're equal, we're going to continue looping around. But here is the problem. So do will expect a Boolean, right? And then in the body we'll expect these four things, right? We'll expect these four things. So that means, yet again, as with like Fibonacci number in do in here, we'll have to push them back. And this is like the main drawback of the let bindings. If you're using them in a while do block, not do end, but specifically while do block, they're kind of difficult to use because you don't really want to remove those elements from the stack. You want to sort of like peek into them, which kind of indicates that the let bindings should be split into two separate features, right? So the current let bindings remove the elements from the stack, but we need to introduce the variant that doesn't remove them. I'm thinking of splitting let bindings into peek, which basically just, you know, binds the name but does not remove them from the stack, and something like take, which basically removes them from the stack. And in the while do block you would use peek, and then in here you would use take. But all of that is a little bit later, right? So I'm currently experimenting with the let bindings because I'm still not sure how they will work out. But yeah, this is the main drawback that I encountered with let bindings. But apart from this specific drawback, they're actually amazing. They actually, on average, make the code a little bit more readable. And we'll look into that a little bit later because I'm going to show another example that actually makes it super easy. All right, so, and the next thing is we're binding those things yet again, S1 and 2, S2 in. And in here, I basically want to truncate the strings. So essentially, I want to say that I'm going to decrement the size of the first string, but I'm going to increment the pointer of the first string. And the same goes for the second string. So S2, 1 pointer plus, and there we go. So we organized the loop, right? So here we're checking that, you know, the characters of the strings are still equal, and here we're advancing the iteration. So after that, we just need to check that both of the strings are empty, right? If they both empty, that means they're equal after this entire process. If they're not, if some of them still have some data, that means they're not equal. So in that case, we're gonna bind them again. S1 and 2 S2, and we're gonna check N1 equals 0, N2 equals 0, and both of them are equal to 0. Might as well actually just indicate it like this. What's interesting is that here I don't really need the pointers, so I can quite easily just put underscore in here, right? And that will ignore these elements, right? So as you can see, it allows you to even like access like not all of the elements, but ignore some of them. So it's already more powerful than usual fourth words, but again, it comes at the cost of you know, a little bit of a syntax noise. So you have to make a conscious decision whether you want to pay with the syntax noise. So yeah. Anyway, what's interesting is that I didn't implement anything special for this feature. So Porth right now just treats underscore as a regular name, and it basically allows the second underscore to overshadow that one. So you still kind of, you can access them, right? You can access them like this, but yeah, usually you won't do that. So it's just like basically it accidentally works. It's a feature that accidentally works. Okay, so let's actually compare these two strings. As far as I know, I already have strEq in the standard library, so I have to call it something like my strEq, right? So this is going to be my strEq, and let's put it like that, and let's print the result. So these two strings should not be equal. And let me see what's going on here. As you can see, it says 0, which means false. And if I have something like hello, hello, it has to be true. So yeah, even though it's a bit noisy, as already said, it's still a little bit more readable because you're being a little bit more explicit with how you manipulate the elements on the stack. So, and again, maybe in the future we're going to introduce something like peek, which will eliminate this thing and which will make it a little bit more like readable, hopefully. I don't know, as much as I don't like word readable because it's a very overused word that doesn't really mean anything anymore, I still think it makes it a little bit more readable, at least for me, right? So I'm primarily doing this thing for myself. So yeah, cheers, by the way. Anyways, so let's take a look at another example, a little bit more interesting example, which actually where the let bindings, in my opinion, kind of shine. And let's implement a function that is called string reverse, right? It will take a string and reverse the characters of the string. So since the strings in Porth are mutable, you can actually manipulate the memory they're located in. It is not like a really intentional, it's just like I didn't really care when I was implementing that. So it is like that right now. Maybe in the future they will become immutable, who knows? We'll see. But for now, you can actually manipulate this memory. We'll see how it goes. Anyway, so we're gonna accept the string. And for the convenience, even though this thing manipulates the string in place, we're gonna still return the string, so I don't have to remember it, right? So I can just reverse the string and print it simultaneously, right? There we go. So let's implement something like this. And let's go ahead and say hello world, right? Then reverse the string and then print it on the screen, and also put a new line in here. How would we implement such thing? Okay, let's bind the components of the strings to names, like, right? So we have a size of the string and the pointer. There we go. So we're gonna basically reverse the string by maintaining two indices, one at the beginning of the string and another one at the end of the string, and we're going to be moving them together towards each other to the center, and while we're moving them towards each other, we're going to be swapping the elements, right? And as soon as they reach each other, the string is going to be swapped, reversed essentially. Okay, so let's actually push the indices on this stack. So the first index is going to be 0. And the second one is going to be n minus 1, right? So here are two indices. And let's organize the loop. So the loop is going to go while this thing is less than this thing. So in that case, we can just use something like over, and just check that one is less than another one. Because again, in while do blocks, is like a little bit easier to use it like that. Okay, so in while end, let's actually bind both of the indices to names, right? As you can see, let bindings can be nested. And furthermore, you can even overshadow some of the names and it's going to work correctly. It's supposed to work correctly. I don't know, maybe there are some bugs, but I have some examples that actually test that. Shadow, I don't remember. So there's a let bindings, local diagnostic. I don't remember local memory nested let. There we go. So I have a test case that actually tests that. Maybe I don't remember. Did I ever test that? I swear to God I tested that. But anyway, so you're supposed to overshadow that. If you cannot do that, it's a bug that needs to be fixed. Anyway, all right. So here's I and J. So and I want to access the characters at I and J. So I'm going to take this string. Which is defined here, right? So I'm just like taking it from here. And then I add I to it, and here is the pointer to the first character in here. So actually, since it's a pointer, I have to do pointer plus, right? And then I'm gonna do J pointer plus. And there we go, I have on top of the stack two pointers, to the left character and to the right character. And now I have to swap them. The question is how I'm going to be swapping them. Let's bind them to their corresponding names. So A and B are pointers. It's quite important to remember. They are pointers to the corresponding ith and jth elements. So let's actually read the first element, the A element, and then the second one. And here's an interesting thing. So on top of the stack we have B, and below B we have A. So that means if I say save that to A, and then save that to B, it will effectively swap them. And that is it. All right, and so now after we did all of that, I have to advance I and J. So I have to increment A by 1, but I have to decrement J by 1. So essentially making them move towards each other. And that is basically it, I think. So after the while loop, I have to drop both of the indices, and that should work. We can try to recompile the entire thing, and I have some insufficient data on the stack. Oh, okay, I see that. So since this entire thing, since N and S removes that from the stack, if we want to return N and S, we have to put them back. And yet again, so here it would be better to have something like pick rather than, you know, take. So because we don't really want to remove that stuff from the stack, but it is right now like that. So we're pushing N and S, and that should be it. And we've got a reverse string. So reversing a string in a stack-based language is rather complicated operation, but notice how I never have to think about what's on the stack. I never had to think about that, right? I never had to put a comment that, you know, where I keep track of the elements. I never have to like think and solve the puzzles, how rot, swap, nip, like fit together. Like I never had to do that. I just like thought about the process and I laid out the process just like that. And the language still concatenative. It's probably a little bit noisier than it could have been if I used fourth style of manipulating the stack, but still, like I didn't really have to think about it too much. I didn't have to solve the puzzle, right? So, but again, it's all of that is kind of subjective. If you got used to the way of like manipulating the stack like in fourth, maybe it's not a problem for you, but it's just like, I find this way of manipulating the stack a little bit easier to digest, for myself at least. So, all right, so that's basically the showcase of the let bindings, and let's take a look at how they're implemented internally, because that's the most interesting part. How do you feed this feature into the current implementation of Porth? Right, because you can come up with any crazy feature you want and spend the rest of your life actually implementing that and fitting that into the language. So how does that fit into the Porth compiler? So I'm going to make a small break and just refill my water, and after that break we're going to look into that a little bit closer. So all right, so the first question that we have is where the elements go to, right? So since the elements are removed from the stack, where are they stored? Well, we push them into the return stack. So essentially, let bindings are a sugar syntax for taking the elements from the data stack and pushing them into the return stack. But on top of that, we have another syntax sugar is the ability to access them from the return stack in arbitrary order, right? So you can access them in arbitrary order from the return stack. You can still access the data stack sequentially, but the return stack like random access. So, and yeah, that's basically the entire idea. And you can even do that in fourth, as far as I know, right? In fourth, you also have the second stack, which is the return stack. And at any point, you can just like take the elements from the data stack and push them into the return stack, like as a temporary storage, and then recover them back. And that's basically a variant of that. That's basically the variant of that, but I think it's a little bit like more like pleasant to work with. And so, yeah, how exactly it is implemented, right? So the Porth compilation, the Porth code actually goes through several phases before becoming an assembly, right? So first you have a Porth code as a text, then the compiler translates it into intermediate representation, which is rather interesting since Porth doesn't have a tree structure, it doesn't have an AST. Even though it looks like it has an AST, it really doesn't have an AST, right? Majority of these things are literally just instructions, right? And because of that, we can just take the text and directly translate that text into intermediate representation into some sort of like a bytecode of the virtual machine of Porth that Porth uses to reason about the program, right? So we have some sort of virtual machine, and that virtual machine has data stack, return stack, the memory, the local memories, and so on and so forth, right? So, and we reason in terms of this virtual machine, and then this intermediate representation gets translated into assembly of this specific architecture, and we support only one architecture right now, which is x86-64, but in the future we're probably going to have more. So yeah, so in terms of the text, we know how this entire thing looks like, right? So this is basically the text. But the question is, what does it get translated to in terms of intermediate representation, right? So what is the sequence of instructions, right, for this specific thing? So to learn about that, let's actually strip down this example, right? So I'm going to remove this thing. Because like if you include standard library, it generates too many instructions, so they're like really difficult to inspect. Right, let's remove all of these examples, and maybe I'm gonna actually turn Fibonacci into the main, right? So that will make it even simpler. Right, there we go. So, and then what I'm going to do, I'm going to inspect the intermediate representation. So Porth has a subcommand called dump, which dumps the instructions of intermediate representation, right? So these are the instructions, and they also have like a location of the tokens that introduce those instructions, and here they are. So we can sort of go through this entire thing. So as you can see, 0 and 1 got translated into OP push integer, right? OP push integer 0, OP push integer 1, and so on and so forth, right? So something like while, as far as I know, it points, I don't remember what it points to. Does it point to the address that it has to jump to? Probably, I don't remember. So there's something in there. So here's the over and then 100. And as we reach, so here's the do, and after do we have let. Right, and after let, let gets translated into instruction called op bind. And this is the new instruction that we had to introduce into intermediate representation to actually implement this let bindings. And as you can see, op bind has an operand, and that operand is 2. So the 2 indicates how many variables you want to bind. And what op bind operation does, it simply takes this amount of elements from the data stack and pushes them into the return stack. That's it. It's a single, like this entire line gets translated into a single instruction, op bind 2. Take 2 elements from the stack and push them into the return stack. That's it. Okay, so the next operation is also a new one. Let's actually keep track of the new operations that we introduced. So here's the thing, new instructions. op bind n. So this is the first one. And the second new one that we can see in here is op push bind 0, right? op push bind. And as you can see here, we're referring to the binding in here. And as you can see, it's A. So it says 0. And another one is op push bind 1 and op push bind 0 yet again. As you can see, well, once we got translated from text to intermediate representation, we don't really have any names of the variables anymore, right? We have these indices, and what these indices represent, that's a very interesting question. Push bind. So essentially, when you have something on the data stack, right? So let's imagine that we have, this is the data stack, A, B, and C. So the top of the data stack is C, right? So it grows basically from left to right. And then we have a return stack. When we push 3 elements into the return stack, we can only push them from the reversed order. So we can take C and push it into the return stack. Then we can take B and push it into the return stack, and A and push it into the return stack. So you see, whatever we had on the data stack, it will be appeared on the return stack in reversed order. Right, and I is basically an index starting from the top of the return stack that addresses the element that you want to push. So op push 0 will refer to A, op push 1 will refer to B, and op push 2 will refer to C. So as you can see, it's basically the index starting from the top of the stack. That's what it indicates, right? So, and it's a job of the compiler that gets text and translates to intermediate representation to figure out the correct indices. Right, so when we have a little bit of a machinery that keeps track of what's the names that are currently bound and how to translate those names into the indices, which is rather interesting, by the way, because you would think that you will have to introduce some sort of scoping and some sort of name tables and overcomplicate the compiler, but in reality, you don't really have to. We keep track of the names by having just a simple name list. Right. So essentially, what do? When we encounter let, we get all of the names from the let, right? And we push all of those names into some sort of like a bind scope table, right? So we have some sort of a bind scope table, and I just push A and B. And then, let's say that maybe I'm going to have C. And then, if I want to figure out the index of a specific name, I ask, okay, so what's the index of this name starting from the end of that table? And then I just use that index in op push bind. So that's it. Like I have just a linear list of names, and I use that linear list of names to map the names to indices for op push bind. So I don't have to have a fancy like hash tables and stuff like that, even though I probably should use some sort of hash table, but we're going to implement hash tables a little bit later, right? So for now, it's fine. It is slow, but I mean, Python is also slow and everyone is happy. So anyway. So that's what we have. We have op bind, which binds n elements, and then you have op push bind, which takes the element by the index and pushes that into the data stack, back into the data stack. All right, so, and here we push a couple of elements more, and at some point we encounter another new instruction, which is called op unbind 2, right? op unbind, and it acts exactly like you would expect. It's like bind, but it removes the elements from the return stack and elements from the return stack and discards them. That's it. So to implement this feature, right, what we had to do, we just had to introduce 3 new instructions. Bind n elements, basically push them into the return stack. Push bind, which takes the ith element from the top of the return stack and pushes it back into the data stack. And then unbind, that will discard those elements from the return stack. That's the entire implementation, believe it or not. That's it. It's surprisingly simple and it's surprisingly powerful. So yeah, that's basically it. And then as we take this thing, we like translate all of these things into assembly, right? We can take a look at how they're exactly translated into assembly. So let's find the generate. Where is the generate? OP. So OP bind. Okay. Oh, that's interesting. So when I do OP bind, I literally reserve some, you know, I think reading this kind of stuff from the Porth code is not particularly convenient. We can just like look directly into the assembly that got generated, right? So we can literally do that. So let's find OP bind. There we go. As you can see, the assembly source code is actually annotated with intermediate representation, their arguments and stuff like that. And also the location of the original source code. So we can actually look at the assembly and figure out from where this assembly comes from, which is very convenient. So essentially, what do we do? Here we take the return stack RSP. So essentially, we have 2 RSPs. The first RSP, so for this who doesn't know, in x86-64, RSP is a register that points at the top of the stack, at the top of the call stack, right? And we use the regular RSP, whatever we have in the RSP register, as the top of the data stack. But since we also have a return stack, we sort of like have a separate region of memory, and we store the top of that region of memory in return stack RSP. So, and we basically juggle between 2 RSPs, essentially, right? That's what we do. So, and here what I do, I just take the return stack top of the return stack, and I subtract 16, basically allocating enough memory for 2 words, right? And then I pop those words from the data stack and I move them into the return stack, essentially. As you can see, like here is me moving, like binding each individual names, right? So to bind a single name, I just have to do pop and move, and that's it. And if I do OP push bind, what I do is just like I take the top of the return stack and I add offset and I just like move it into the data stack. Right, and unbind, as far as you know, unbind simply deallocates, you know, the memory that was allocated by the previous bind. So that's literally it. So it's surprisingly simple feature, right? You don't really need to have anything complicated to implement it. I think the most complicated thing about this feature is figuring out how particular names bind into the indices, into the corresponding indices. I think this was the most complicated thing, and even by itself, it is not that complicated. Right, so we can even take a look at how exactly we, you know, translate all of that. So if I have something like A, B, C, then I have something like BC in. So let me actually enable Porth mode. Right, so BC and that then another D, right? Something like this. Okay, so this is how it is going to work. So I have a scope table. So I'm starting to parse this entire thing, and I found A, B, and C. I push A, B, and C into the scope table, and as already set, to translate now name B to the corresponding index, I have to find that B starting from the end. So, right, so the indices of this thing is 0, 1, 2. That means the index of B is going to be 1. So B gets translated to 1. But it's not going to really work for A. Right, so the index of A is not particularly 0. So here is where the interesting part comes from. So essentially, if on the data stack you have A, B, and C, and you move them into the return stack C, B, A, right, in that case, oh yeah, I screwed it up. So the indexing has to be like actually in a reversed order, because we're like looking at them from reversed order, right? So the index of A has to be 0. But in a scope table, starting from the right position, it's going to be 2. Right. So essentially, once you pushed this pack of names into the scope table, you have to reverse them, right? You have to do something like this, and then this is going to be a correct thing, right? So now A is 0, B is 1, and C is 2, exactly like they are in the return stack. So essentially, in the scope table, you have to mimic their order in the return stack. So, and then we open another thing and we push B and C, and again we'll have to swap them like that. So now we have so it's 5 4 3 2 1 0 like this, and now you translate B to 0, but as you can see, B sort of overshadows the B from the outer one. But since we're searching from the right and always stop at the first name, you can overshadow the names like that, right? So, and then you have a D, and D becomes something like this, where you have like that. So, and after D is closed, we simply remove the D, offsetting everything back. Right, and then after you move out of this entire thing, you remove this thing, and this becomes 2 1 0. So, and that's basically by maintaining this scope table like this, we can quite easily figure out what the names map, what indices the names map to, right? Without having like anything super sophisticated. You just like have like the stack of the names, right? But you have to be careful with the order, right? So you have to mimic the order of the elements on the return stack. So the scope table literally mimics how the names are laid out in the return stack. Hope that makes sense. I hope that makes sense. In any case, if there's something is not particularly clear, you can always check out the source code of Porth. You can find it in the description. So, and we have functions like scope. So I forgot how it's called. Table. It's called bind table, right? So the bind table push. So that's cool. So bind table push, yeah. So here is the bind table lookup. So this is how we look things up, and here is the thing that reverses stuff around. Yeah. Yeah, so this is basically the algorithm that I was talking about. So the function is called parse bind list, right? It takes the lexer, which spits out the tokens, and then it takes the tokens until it encounters in, right? Because the entire thing ends with in. As you can see, it ends with in. And as it encounters names, it pushes them into the table, right? It pushes them into the table. And then at the end of this entire thing, it reverses top elements on the stack like that. So that's basically what it does. I think this is the most complicated thing in the entire implementation. And again, by itself, it is not that complicated, right? So you just have to mimic the return stack. In any case, that's pretty much everything I wanted to say in this sort of like a report about this feature. I'm going to be using this feature more to figure out its drawbacks and like think about how to fix them. And I see you on the next Zodin session. How about that? So yeah, see you around. Love you all.